1. So this guy right here is not bypassed. This one's a little easier to me. Of course, hopefully they're easy to me, right? And this is what I think is so cool about this, man. This is right out of DC. It gives you a reason of learning series and parallel circuits. When you're in DC, what do those series and parallel circuits do? What work do they do? In DC, what work do you get out of those things? Heat. That's it. You get heat. So y'all looking at the basic makeup of a heat. We get into here though, we learn that we use those resistors in series and parallel to set the bias. And we look at this like it's two different circuits, right? All the resistors, the loads are all what? 10K? Okay. So the first thing we'll do is calculate VB. So VB would be equal to 10K divided by 78K times 20 volts. And mark off the K, so that's 10K divided by 78K. Okay, so VB equals 2.6 volts. Everybody okay? Just series circuit, right? Even if you didn't know to do that, you could calculate current, but this formula is great because you don't have to even deal with current. I mean, you just got it, just like that. Okay, then I know VE is pretty easy to do. This is going to be 2.6 minus 0.7, which gives me what? 1.9 volts. If I know VE and I know RE, I can calculate IE. So IE would be equal to 1.9 divided by 1.1K. Can't drop the K here, guys. What do we got? About 1.23 milliamps. What we got? 1.7 milliamps. Are we okay so far? Okay. Then I can calculate VR3. VR3 is going to be, because we're going to assume that IE and IC are equal, right? Even though we know they're not, they're 99% the same, right? So we're going to use IE for IC because they're so close to each other. So what I'm going to do is I'm going to calculate VR3 is going to be equal to 5.9K times 1.7 milli. So what we got? What's that? 7.3? Oh, 10. Like 10 point. Okay, 10.10. 03 is, what's nice about this, we can do a lot more rounding here. This guy here is biased really, really good. What we're shooting for on these things is we're shooting for 1/2 of VCC. And so what would be 1/2 of 20? 10. So we're biased right in the middle. So that means I can get as much positive as I can negative. Does that make sense? So when I bring an input signal in, I can swing it positive just as much as I can negative. Then I need to calculate VC. So VC is going to be equal to 20 volts minus 10.03. What we got? Huh? Yeah, 10 bucks. That look good so far? Everybody okay so far? What laws have we used so far? We used the voltage divider formula, which you should have learned in DC. Here we used a little bit of Kirchhoff's law, right? You understand that 7/10 of a volt, we subtract from there because we know how much this guy here drops. So we know what's there and we know what this drops, so we can calculate. That's Kirchhoff's voltage law, right? This is Ohm's law. This is Ohm's law, and this is Kirchhoff's law, voltage law for series circuits. Okay, so everybody okay so far? Oh, VCE, so voltage collector to emitter, would be equal to 10 volts minus whatever's on the emitter, 1.9. So what's voltage collector to the emitter? 8.1. So we know it's operating in what region? Active region. That makes sense? Okay. What are we looking for on this? And this is going to be on the test, by the way. If it's less than 1, we say it's what? Saturated. If it's equal to VCC, it's cut off, right? And if it's between 1, then it's inactive. Okay, so what do we need to do now? Need to calculate voltage gain. So here we're going to load this thing. I mean, this is, the book don't show you how to load it, but I wouldn't have an amplifier if I didn't get work out of it, right? Y'all understand that? So we'll come over here and we'll calculate, so the formula is AV would be equal to, we say it's R out over, and this is going to be RE because it's not bypassed, right? So we got to calculate R out. So R out would be equal to what? Because of bypass, that's a bypass capacitor. So when we talk about bypass, we don't use RE, we use RE prime. So this is not bypass. So what we do is we sacrifice gain for input resistance. Okay, so if I've got a little antenna up here sticking up in the air, and I bring that into my first amplifier, do we want that thing to have low impedance or high impedance? Huh? If I come over here and this is my antenna on my car radio out there, the first amplifier I go into, do we want it to have low impedance or do we want it to have high impedance? How much of a load can an antenna drive? Can an antenna drive a speaker? No. If I want, low impedance means it's got to provide a lot of current. High impedance means it don't have to provide a lot of current. So my first amplifier is supposed to have extremely high what? Input impedance. Extremely high. Then what I do, what we do is we sacrifice gain for a higher input impedance. So what happens if you don't bypass RE, then RE is seen as times beta. That's what it's seen as. So if you've got a beta of 100, then the input sees that as over 100K of resistance over there. But if I don't bypass this, we sacrifice what? Gain. So we sacrifice gain for high input impedance. But we don't get much gain. And then I might run that through several amplifiers, and what I do is I start lowering my input impedance. I start lowering my input impedance. I start lowering this and I start lowering that. So eventually when we drive our load, what do we want this guy right here to have, the output there? We want it to have high impedance or low impedance? Very low, because now it's driving a load, right? You understand? So what we do is we go through stages of amplification. In fact, in radios, if you look at the schematic, odds are they don't use a bipolar transistor because bipolar transistors, we can't get an extremely high input impedance. But when we get into FETs, we'll learn that. So most of the time, the input amplifier is a FET. And then we'll start off. We won't bypass them. And then as we go along, we'll start doing what? We'll start bypassing them, and eventually we'll get an extremely high current in. So that's why we go through amplifiers. That makes sense? So what we do on this, if we don't bypass it, what do? Well, we increase the input impedance. That's what we do, which means whatever's driving this over here don't have to provide as much current, right? We still get a gain, but we're not going to get these gains of 80s and 100s and stuff like that. But we still can get a gain of 4 or 5, right? You understand? If I get any gain at all, then I can take that gain and feed it into my next amplifier stage, right? Does that make sense? So all these amplifiers that we run into, these audio amplifiers, go through stages. I mean, how much of a load can your CD player provide you can't provide hardly any, right? You understand? So what do? We amplify it through stages. So that's what we do. So when we don't bypass it, we do what? We sacrifice gain, but we increase our input impedance. If we bypass it, we get a lot of gain, but we sacrifice input impedance, right? So it means whatever's driving a bypass transistor has got to be able to provide more current than an antenna can. So is that okay? Understand? Okay, so this is not bypass because these capacitors right here, C1 and C2, are called what? What do we give? What these are called coupling capacitors, and that capacitor that goes around R4 is called a bypass capacitor because it makes the AC bypass RE. So what's R out equal to? So there's my output right there. I see a dot. So my output is so the transistor is the source. Y'all understand? It's the source of the AC. So that would be like me coming up here and doing this. And then I hit this dot right here. And as soon as I see a dot, that probably means what? Parallel, right? So there's my dot. Here's my source. Here's my dot. What do I see? Well, I see R3. And what do we see this way? We see R the load. I'm ignoring, this is AC. This has nothing to do with DC. This is AC. And what does the AC see that thing as if we choose the right size? What do we calculated X of C the other day, and I don't forgot 60 hertz, and it was like 20 ohms because we was using a 10 microfarad capacitor, right? Almost nothing. So AC basically you don't see that capacitor. So over here this would be a 10K. Can y'all calculate that circuit right there? That's just what? It's just a parallel circuit. So you can use the product over the sum, or no, it's not. You can't be 5.9K. It's got to be smaller than the smallest. Parallel circuits. One of the rules right off the bat is it's got to be what? Smaller than the smallest. Series circuits have got to be bigger than the biggest. Parallel circuit has to be smaller than the smallest. So it can't be 5.9K. You can use product over the sum if you know how to use parentheses on your calculator, or you can use that reciprocal of the sums of the reciprocals. Can't be ohms. Normally, if I have K and K, I'm not going to come up with ohms, right? You understand? Normally, if I have K and K, I'm going to come up with. No such thing as point. And for technicians, it's no such. For us, it's no such thing as. What we got? Probably 3.7K. By the way, when we start doing this, if you come up and give me that, then something's wrong because here we're using legal engineer notation, right? Somebody, yeah. 3.7K ohms. Are we okay? Okay. So now I can calculate the gain. So the gain would be equal to R out, which would be 3.7K divided by RE, which is 1.1K. Of course, K is going to cancel out, so we're not going to get a lot of gain out of this thing, but we don't expect that, right? What's our gain? A little over 3. Huh? What's that? And what unit is that? No unit. It's just a gain, right? Gains don't have units. And like we said, we could do dB, but dB is not a unit. dB is like what? It's like engineer notation. It's a way for us to represent big numbers and little numbers. Okay, guys, what else do we need? So what would be the dB gain here? What would be the dB? What would be the dB voltage gain? Okay, but I'm asking something else right now. I know. So what would be the dB? I'm trying to bring up my calculator. Okay, that one. I need to go here. Get my calculator. Okay. Wait, there it is. Okay, so how would I calculate the dB gain right here? Just went over this last class. No, this is voltage. This is voltage. So I'm going to take 3.36, and I'm going to take the log of that right off the bat, and then I'm going to multiply this times 20. So it's 10.5 dB. I do that right? 3.6, then take the log of that, and then multiply that times 20. And why 20? Why did I get a different answer? 3.36 log times 20. 10.6 dB. Yeah, 10.5, I'm sorry, dB. Now why 20? Because it's voltage, right? Power is 10. Okay, so RE prime, which we didn't really need, I'm just getting you in the habit of calculating it. RE prime would equal to 25 millivolts over IE. What's IE? 1.7 milliamps. So we didn't really need RE prime on this circuit, but like I just wanted y'all to get used to calculating. So what we got? What's that? And this is, what's the unit? Ohms. Sound like a question there. Yeah, it's ohms. This is RE prime. So up here, instead of using 3.7, if we bypassed it, we would use 14.7. Instead of using 3.7K, if we bypassed it, we would use 14.7 ohms. You can see how much more the gain would be. But we sacrifice input resistance, right? Okay, guys, anything next? Anything else I want to jump start for? What's that? AI? What's that? Okay, was there anything else on this circuit that y'all need to solve? Okay, so what are these? So what's the symbol for gain on these amplifiers? A. Okay, so what would AB be? Okay, AB would be what? Okay, AI would be lowercase to current gain, and AP would be what? Power gain. Now we got a little problem with common emitter amplifiers. Normally, when we calculate gain, we can use the voltage gain to get the power gain. We can use the current gain to get the power gain. The problem is with a common emitter amplifier is that we get both voltage and current gain. and the voltage gain and the current gain are not the same. So that means normally we would say, you know, what did it come up and give us a while ago? 10.5 dB. Normally that would be the gain. That would be the gain period. But that would be if we didn't get a voltage gain, or if we got a current gain and not a voltage gain, or if we got a voltage gain and not a current gain. But a common emitter amplifier gives us both a what? A current gain and a voltage gain. So I'll show you how to do this. It's not really hard. It's still using our laws. I mean, this probably won't be on the test. I'll just probably ask for dB on whatever gain you calculate. Right now, common emitters, we'll look at voltage gain. But what we have to do is, first of all, to calculate our current, what we're trying to do is we've got some type of source over here giving us a signal, right? So it might be a DVD player, it might be an antenna, it might be something providing gain to this current. Now, why common emitter amplifiers are so dang inefficient is that we got to have these things consuming power even when we don't even have a source attached to them. They sit here and consume power, right, to support that bias. So there's no such thing as an amplifier that is 100% efficient. We always lose. And the amplifier is not creating power. What is it doing? So the amplifiers don't create power. I don't call a transistor a power supply. So where does the power come from? Where does the power always come from? I just got it out of my mouth. It comes from the power supply. And that's why we call them power supplies. So all a transistor does is manipulate the power that's available from that power supply. So I could go out there on your radio and I could unplug it and go get a couple little 9-volt batteries and hook them up. That's 16 volts. As soon as you hooked it up to that dang radio, those batteries would be dead because those little power sources don't have enough power, right? You understand, to support your radio. Now your big old car battery does out there. You know, that sucker's rated at a couple 100 amps. So by George, it can provide the power. Your alternators are rated in, you know, about 100 or 90 something amps. They can supply the power. So all these amplifiers do is they do not create power. What do? They control it. They control the power that's available from the what? We call these guys what? Power supplies. We don't call them current supplies. We don't call them voltage supplies. We call them power supplies. And then our amplifiers, all they do is just do what? They just control that power. Yeah, what surprises me sometimes, people will come up with more voltage drop in a circuit than you have right there. You know, you can never drop more voltage that's available than the source. I've seen people in DC come up, say, 10 kilovolts dropped across a resistor, and there's only 5 volts applied to the circuit. DC is, I don't know. Y'all probably ran into some of those people. So first of all, we need to figure out what the load has to provide. So here comes the AC. And what does it do, guys? We went over this a couple times. What does it do? It comes up and does what? Goes that way. That does what? Goes this way. Does what? Okay. Everybody okay? So to calculate IN, I got to know RN. We're going to ignore the capacitor. Why are we going to ignore the capacitor? Oh, yeah, it has no opposition. So I'm going to say Rn would be equal to 1 over 68K plus 1 over 10K plus 1 over beta. I'll give you the beta, 50. Now you probably have to do this one first, right? times RE. Dang it. Close my calculator out. So 68 times 10 to the third reciprocal plus 10 times 10 to the third reciprocal plus, I'm going to close parentheses here. If you do this one first, then you don't have to do parentheses, right? It's 50 times 1.1 times 10 to the third equals reciprocal equals reciprocal. 1.8, 1.82K or 1.8K. That sounds a little low. Sounds like I did something wrong. Because all these are up in the tens of Ks. It's supposed to be smaller than this, but look at that guy right there. That's 68K, that's 10K, and this right here is 50-something K. So it looks like my answer is, mine is really wrong because I've got a -5. So let me do that again. So sometimes you can tell your answer is wrong, right? So let's do this one first. So I'm going to say 50 times 1.1 times 10 to the third equals, there we go, reciprocal plus 68 times 10 to the third reciprocal plus 10 times 10 to the third reciprocal equals reciprocal 7.5K. And that concerns me too, where people comes up with a wrong answer, and just learning your little rules of thumbs, you can tell right off the bat they're what? They're wrong. And all it does on parallel circuits is just hit the reciprocal when you didn't mean to or something like that. Okay, so 7.5K. It's close enough for us, right? Okay, so now I need a current. I need a voltage because I can't calculate. So I is equal to V over, we're going to say V over Rn. That's going to give me my input current. But what? What's the problem? What's that? Don't have voltage. So what do you think we're going to do? I mean, it's an amplifier. It takes what it gets and amplifies whatever it gets. Whatever it gets. So what can we do here? Just throw in something. We don't want to saturate it, so normally we use maybe 100 millivolts. So I say IN would be equal to 100 millivolts over, what do we get, 7.5K. So what's IN? And that's what's neat about an amplifier. It amplifies what it gets. So if you don't have a voltage, what can you do? Just use one. What we got, guys? We're going to be down in the microamps, but it's okay. Huh? 1 point what? 33 watt. Milli by K. It's going to be at least micro, right? We got microamp. Microamps. Right? Milli divided by K. That's going to be to the 6. I'm not doing this. I can break up my K. What? 15.3? 13. Okay. Okay, so I got 13.3 microamps in, just making up. Okay, guys, what do I need to do now? So I come over here, and I know my output voltage, I'm sorry, my I out is going to be equal to V out over R out, or Z out. We've already calculated Z out to be, where did we calculate that? I erased it. 3.7K. Okay, what do I need to do now? I know I got 100 millivolts in. I just made that up. How can I calculate V out? What do I know? I know this right here. What is this? That's the voltage gain. So if I'm putting 100 millivolts in to calculate my output voltage, I just take my input voltage and multiply it times the what? Times the gain. So V out would be equal to 100 milli times 3.36. Y'all following? 336 millivolts out. We okay? We could have chose a lot higher voltage. Is that right? Huh? Okay. All right. So now I can take V out. So I out would be equal to V out, 336 milli, divided by 3.7K. Is that going to be equal to? Huh? 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 What's that? Okay, so what's my current gain? AV. I'm running out of room. How do we calculate gain? How do we calculate gain? Not in or out over in. Yeah. So I take 91 micro divided by, what was my N? 13.3 micro. Of course, the micro is going to cancel. So AV would be equal to what? I mean AI, sorry. We got a 6.8. We got a 6.8 current gain. We got a 3.36 voltage gain. So what would be my power gain? How do we calculate power? Huh? Good. 3.3. That's my voltage gain. I multiply that times my current gain, and that'll give me my power gain. Not a bad power gain. 23. So we got a power gain of 23. So what we know, and the problem we have with a common emitter amplifier is you get more than one gain. Does that make sense? So you have to do it a little different. So we got a current gain, we got a power gain of 6.8, we got a current gain of, we got a power gain of 23, we got a current gain of 6.8, and we got a voltage gain of 3.36. So that's the first circuit. Anything else? Of course, we could do dB on our power. So dP on our power would be, 23 log of that times 10, right? Okay, any more you want to work? One of the bypass. Number 4. Everything's the same, except here we use RE prime instead of using RE. And what's important, of course, is that you understand the formula sheet, right? 1, 2, 3, 4, 5. So this guy right here. This guy right here. This is a PNP. Everything's exactly the same, by the way, except your voltages are going to be negative instead of positive. Okay, first thing I calculate is I calculate VB. So VB is going to be equal to 10. Oh, this is 10K, but the K is going to divided by 11.8K times 20. So what we got? What's that? Minus 3.1. All these voltages are minus, right? VE would be a minus 3.1 minus 0.7. This is, huh? No. Well, we did something wrong because this is the what type? Well, what type of transistor is it? So that means for this thing here, for this thing to work, the emitter's got to be more positive than the base. So we got the base set at minus 3.1. So if we say the emitter has got to be minus 3.8, that puts the emitter more negative than the base. So it's probably better because what you do is you change the sign and add because these are sign math. The best thing to do here is just do your math without signs, but put signs on your answer. Y'all understand that? Because I knew that was going to happen because, because the math, but you got to understand this is a PNP, and this guy right here's got to have less voltage than that. It can't have more voltage because we go through a voltage drop. So I can't say I got more negative voltage here than I have right there. I got to have less negative voltage. So the best thing to do on PNPs is just do your math without signs, and then put the sign on the answer, right? Okay, so what we got? 2.3? Huh?
Yes.
And then IE, of course, current has no, huh? 2.4? Okay, then IE has no sign, so it's going to be 2.4 divided by 200 ohms. What's that? 200? 12. Sorry. I can see that. That's one of those you can do in your head, just about it. Okay, now I can calculate VR3. Now, voltage drops have no sign either, right? You understand? It's not going to drop it. I guess it would. So VR3 would be equal to 12 milli times 1K. So it's going to drop 12 volts. And then VCE, VC is going to be equal to 20 minus 12. What's that going to be? Yeah, but it's going to be minus 8. And this is what I'm saying. What you need to do is just do your math and just make your answers what? Negative. And that way you don't have to. So what we're doing is we're doing what we call absolute values. You know what absolute values are? That's numbers disregarding the sign. Okay, so now I can calculate voltage collector to emitter would be equal to 20 minus, voltage collector to emitter would be equal to the voltage on the collector. Voltage on the collector, 8, minus the voltage on the emitter, 2.4. And what do we got? By the way, here voltage on the collector is equal to 8 volts. What would we like it to be for a Class A amplifier? Huh? Okay, so what happens is, let's do this. Let's pretend this is an NPN. Okay, so this is the voltage I have to work with. I have 20 volts, and then I have 0 volts. Y'all understand that? And what I'm trying to do is I'm trying to amplify something. If my output, if I bias it up into here, and my output starts going to positive, it's going to do what? It's going to clip it, and then it might come up and do this. So I've got plenty of room on the bottom, but I don't have plenty of room at the top, right? You understand? So that means if I bias it toward cutoff, then the tops are going to clip before the bottoms. And the maximum you can get in depends on where you cut off at. You're either going to saturate or cut off. Well, what if I bias it down here? And I'm trying to do the same thing. Well, now what's going to happen? Now it's going to give me this, but when it goes positive, it's going to do what? I mean, you can't go down below 0, and you can't go above the source. So where would we like to bias this at? Where would we like VC to be? Huh? In the middle. So I would like VC to be sitting at, I would like it to be sitting at 10 volts. VC, not VCE, VC, because we're developing it across those two resistors, right? You understand? Now, of course, we're not going to get that because of this resistor right here. But at least we got a shot at it if we put it right in the center, right? You understand? So this guy here is this guy is biased towards saturation. So the closer it gets to 0, this is toward saturation. The closer it gets to 20, this is toward cutoff. We would like it put it right in the center. What prevents me from putting it right in the center? Nobody's got a guess. Somebody take a guess. Nobody's going to take a guess. This right here prevents me from putting it right in the center. Standard resistors. I've got to choose what? Standard resistors. Right? You understand? And I'm fooling around with a lot of stuff. I'm fooling around with input impedance, output impedance. I'm trying to make it match my previous amplifiers, and I'm trying to do this with what? With resistors that I didn't pick. I got two options. I can use rheostats all over the place, or I can use these resistors that cost less than a penny a piece. What are you going to use? Yeah, you're going to use the cheapest you can get by with. But what you do is you sacrifice. You do the best you can, and then you limit the input. And that's another thing that would limit the gain. So the gain is not set by, it's set by the amplifier, but it's set by which one of them clips first. So whichever one clips first, that would determine the maximum input you can put into an amplifier. And very seldom do they clip at the same time. Either they're going to be biased a little toward saturation, or they're going to be biased a little toward what? Cutoff. And wherever you bias them at, that determines your maximum input voltage. It's not going to change your gain, but it's going to change your maximum input voltage. Because you don't want to clip, because as soon as you clip, then you create what we call distortion. Sure. Let's go ahead and finish this one. I mean, good gracious, we're only what? How many steps away? Well, we're not going to do all the current gains and stuff like that. That's not going to be on the test. But we do need to do, okay, so what do we need to calculate now? Oh, we need to calculate gain in circuit, right? Isn't that the next thing? RE prime. To calculate the gain, we got to calculate RE prime. RE prime would be equal to 25 milli over 12 milli. What's that? Yeah, that's almost nothing. You can see the higher this guy is, the lower it is. But to get that, we had to choose these resistors have to be very small. So we got a real low output impedance to get a real high gain. Does that make sense? And when you're designing these things, there's a lot of considerations you need to take. We don't want a low impedance amplifier to feed a high impedance load, right? Does that make sense? What are we shooting for? What did we talk about last class? We called it, it's called impedance matching, right? When your impedance is matched, you get what? When your impedance, that sounds like a great test question. When impedance matches, what do you get? You get maximum what? What are we trying to get out of our amplifiers? We get maximum power transfer. You get maximum power transfer. Don't you remember we threw the little resistors out there and I said, okay, I got a 100 ohm source and we're going to do 1K, 110, and we got the maximum power transfer. If you had a 100 ohm source and you had a 100 ohm load, you got the maximum power to the load, right? And that's what we're trying to do. We're trying to get the maximum power transfer. When you get maximum power transfer in a communication channel, when the watts match, when the impedance is in the channel match. So that's important. So I don't want a low impedance amplifier to feed a high impedance load. I want a low impedance amplifier to feed a low impedance load, right? Okay, so what would the gain be? We need to calculate R out. R out is going to be equal to 1 over 1K plus 1 over 10K. The output impedance of the amplifier is real easy to see. This is the output impedance of the amplifier, right there, at RC, right there. So we're not going to get maximum power transfer with this one. So what's R out equal to? Eight, 900 ohms. I'm listening. What's that? What's what? Yeah. Okay, so now I can calculate AV. AV would be equal to 909 divided by 2.1. So what are we using now to calculate our gain? Yeah. So if we're not passed, if we don't bypass, we use RE. If we do bypass, we use RE prime. So what's our gain now? What's that? So we'd drop this by a factor of 10. If we didn't bypass it, we'd use RE, so it'd be 200 instead of 2.1. And what's the dB? Give me the dB and we'll take a break. This is voltage gain, so we're going to multiply it by what? 20. So 433, I take what? Log of that times what? 20. That's 52.7. And gains have no units. I don't know, that's one of the hardest things for people to comprehend. They're just so used to putting volts and amps and watts that they think if they throw a number out there, they got to put something out there. But gains have no units, right? Okay, guys, you'll take a break. I mean, they're all pretty much well the same that I can see. Once you get one of them down, so the only difference between the two is what? Basically is whether you use RE or whether you use what? RE prime. When do you use RE? When it's not bypassed, when you use RE prime. When it is bypassed, right? You understand that? I said that right? When do you use RE? When it's not bypassed. When you use RE prime. When it is bypassed, right? I did say it right that time. We got 3 ways we can connect transistor amplifiers or bipolar amplifiers. What's the 3 ways we can connect? Yeah, bipolar. 3 ways we can connect. Common base, common emitter, common collector. Common base is real hard to see because on common base what we do is we input on the emitter and output on the collector. So it looks real strange. And you don't run into that much, but we don't teach them, but we don't teach them in this class anymore. And I don't know if you're going to run into them or not, but so if you ever, you will in some communication circuits. Oops. We'll do it in a voltage divider bias. So here's the in. Here is the out. So this is common base. So we have very, very low input impedance on a common emitter amplifier, a common base amplifier, because the current is basically coming from the source. But what we get out of it, so a common emitter has very, very low input impedance, and then we run it to a pretty high collector resistor, so it has a real high output impedance. So we can get voltage gain out of a common base, but we can't get current gain. Does that make sense? In fact, the current gain is less than 1 because this has got to support this guy right here too, right? You understand that? We use this, but what's good about a common base is, of course, some of y'all all had AC, right? What's nice about the common base is this is my input capacitance right here. Besides for this, we have very, very low input capacitance. And what that means is we can operate these things at extremely high frequency. So their upper cutoff frequency is extremely high, and that's the only advantage these guys have. Extremely high input resistance. Extremely low input impedance, which means we can get a higher frequency. Does that make sense? But notice what you're doing. You're inputting on the watt, on the emitter. You're outputting on the collector. And the input signal would be applied right here. And then if we want to get a higher current, if we want to get a higher voltage gain, our bypass capacitor would be over here on that resistor right there. So it's really strange, isn't it? So you're not going to run into this guy very often, so we're not going to talk about it. But the characteristics of it, what's the characteristics of it? Very low input impedance, very high output impedance. We can get a voltage gain, but we can't get a what? Current gain. And where do they apply? Well, they apply on extremely high frequency applications. But your source is going to have to provide, not only, it's going to have to provide the load current. So your AC is coming from the load. So if you need 1 amp out here, your source is going to have to provide what? 1 amp. So the other guy that we're going to run into a lot that we need to understand is the common collector. Also referred to as the emitter follower. And we'll show y'all voltage divider bias. And this guy's actually easier to calculate than the common emitter because we don't have a collector resistor. So how do we figure out what leads common? We look at what we input on, we look at what we output off, and the other lead is common. So on a common base, we input on the emitter, we output on the collector, so the base has to be common, right? Now, we're not talking about common to DC, we're talking about common to AC. So common collector means I'm going to input on the collector. I'm going to input on the base, and I'm going to output on the emitter, and we'll put a resistor down here right now. So that means the collector is common to the AC signal. We never bypass, you'll never see the emitter resistor bypass because now we're developing the load across the bypass. Does that make sense? We might put a capacitor right here, so we never bypass a common collector. So let's say this is 10K. Normally these are pretty close to the same size. And let's say this is a 1K. And let's say I come up here and I put 20 volts on it right there. Okay, guys, what would VB be? Don't even know calculator. What would VB be? 10K, 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 20 volts. Both resistors have to drop an equal amount. They have the same current. Both of them have to drop the equal amount. So our base voltage will be set at 10 volts. Right? Now, of course, it's not going to be at quite 10 volts because this resistor here is going to conduct just a slightly more current. Because when we bias this thing on, remember your emitter current is flowing through here. I mean, your base current is flowing through that resistor right there. So the top one's going to drop a little more voltage. If you wanted it exactly in the center, you got to play around with these resistors a little bit. So I mean, what do we have sitting on the emitter right here? 9.3 volts. Hadn't even picked up a calculator yet. So we're biased a little toward saturation, but that's okay. Or I'm sorry, a little toward cutoff. This guy, the input and the output are in phase with each other. So I come in here, I can put a lot of voltage in on this thing. Let's say I come over here and put 4 volts, or let's say I put 4 volts peak to peak. What would be my output voltage? We've already taken out the 0.7 of a volt. The transistor's turned on. And this is called an emitter follower. Why is it called an emitter follower? Because the emitter is following the base. So that means if I put 4 volts peak to peak on the output, I might be getting 3.9 volts peak to peak out because we can't get, because the only voltage we lose is by RE prime. That's the only voltage we lose. So we never, ever, 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 ever will get exactly the same that's on the base on the emitter. The emitter will be slightly less. But these guys right here have an AV equal to approximately 1. You can't get any voltage gain out of these guys. Can't get voltage gain out of them. So what kind of gain are we going to get? Current, yeah. I mean, good gracious, my input, if this guy here's got a beta of 100, then my input resistor, then Rn is going to be 1 over 10K, 1 over 10K plus 1 over 10K plus 1 over 100K. What would be my input resistance? Reciprocal of that, right? It's going to be less than 10K. It's not going to be much. This guy right here we can pretty much ignore. It's going to be pretty close to 5K. What is it? Yeah, in parallel circuits, it's going to be a little less than 5K. 4 point, what is it? 10K and if it was 10K and 10K, it would be 5K, right? And then we got 100K in that. So what does it come up and give us? Around 5K. You know, we talked about the 10 to 1 row, right? We told you about 10 to 1. Yeah, if you got a 10, something that's 10 times bigger than these resistors right here, then usually we can basically ignore that. So we got 5K input, we got 1K output. Here's my output impedance. Here's my input impedance. So our output impedance is a lot lower, but we have the same voltage, so we definitely get a current gain out of this. By the way, I could come down here and do this. I mean, I could come up here and do this. Let's say I drop this down to 100 ohms. What would my output voltage be? It's going to be 3.9 volts, right? right, until the transistor either saturates or cuts off. So we can have extremely low output impedances on these things. They give us pretty high input impedance. They give us a real low output impedance. These guys are your current drivers. These are the drivers right here. These are the guys that drive low impedance loads. Low impedance means it's going to need a lot of what? Going to need a lot of current, right? You understand that? Need a lot of current. So these guys give us tons of current gain, but we don't get any voltage gain. But I can get my voltage gain out of the way with common emitters, right? You understand? So I can get plenty of voltage gain with a common emitter. It's just when I need to drive those low impedance loads, I mean those speakers or those guys that require a lot of current and a lot of power. So power means current, right? Not only does it mean voltage. So I don't get any voltage gain out of the thing. In fact, the voltage gain is going to be less than 1. But if I put 50, I can't put 15, but I can put 10 volts peak to peak over here. I'd get 10 volts peak to peak out, right? You understand that? Or close to it. We'll never, ever, ever. So when we say it's equal to 1, it's not, it's always going to be, it's alpha. It's going to be less than 1. It's the alpha of the transistor. So this is where that alpha comes into play. Remember the alpha, which is equal to beta over beta plus 1. Y'all remember that formula? It should be on your sheet somewhere. So they don't give you the alpha of the transistor, they give you the beta of the transistor. Because the alpha is so easy to calculate, right? So guys, I mean, these are the guys. So what we'll do, this is what goes on in your stereo right here. But if it's Class A is only around what? 25% efficient. You remember that? Or what's Class B? Around what? About 75% efficient. So what I can do is I can use 2 Class B amplifiers. So what I'm going to do, and they're going to be connected common collector. So these are the outputs of your stereo right here. These guys right here. So I'll come over here and we're going to do it a little different. We'll have to talk about this later on. We'll hook this up. And I'm going to come up here and I'm going to do this. Oops, sorry. So up at the top, I'm going to use a NPN. On the bottom one, I'm going to use a PNP. I'm going to connect the emitters together. I'm going to come over here and connect this to like a negative 20 volts. I'm going to come up here and connect this to a positive 20 volts. I'm going to come up here and put this on here like this. These are emitter followers, right, or common collectors. So it means if I put 20 volts peak, if I put, I'm not going to put 20 volts. Can't get 20 volts. Let's say I put 9 volts or 18 volts peak to peak. Well, when this thing goes positive 9, it's going to cut this guy on and let this guy go through, right? And then when I turn this one, this guy is going to turn off and this guy is going to turn on. And the problem is we're going to end up with this right now and we're going to do this. And what is that right there? Is that DC or AC? That's AC. So using these guys, I can output AC. I don't have to go, and then I can come over here and hook this up to an 8-ohm speaker. And these are the guys right here. This is what your stereo has in it. This is what your audio amplifiers have in it. In your TV and all kinds of stuff they use. But this is a Class B, and this is a Class B, but it gives us an output that appears to be a Class A, right? You understand? So we call this guy what? This guy called an AB. So just about all your outputs on your stereos and stuff like that are AB amplifiers. All we got to do right now is figure out how to get rid of the what? The crossover distortion. You know what causes the crossover distortion? Nobody, take a guess. What do I have to put on the base before the transistor even turns on? Huh? No, y'all not listening. What do I have to put, what voltage do I have to put on the base before the transistor turns on. About 7/10 of a volt. So my input is swinging right here, right? I take 7/10 of a volt to turn it on. So my output's going to be sitting here because neither one of us is on, then it turns on. And then it goes down to 0. What do we have to do to get the PNP to turn on? This has to get down to what? Minus 0.7. So what we got to do is figure out a way to get rid of that crossover distortion. So if I take two transistors and just hook them like this, we'll get that crossover distortion. I'll hook this up and let y'all, just the way it is now, and then later on we'll look at how to do how to get rid of the crossover distortion, and then we'll look at some actual power amp outputs, and you'll see the same circuit. It's not that hard. Just use a little diodes, a few diodes. So y'all go ahead and go to lab. What I'll do is I'm gonna come up here and hook this circuit up, and when I get it hooked up, I'll show it to you. A 2N, I'm gonna get a 39. These need to be max pairs, right, or complementary pairs. So I'm gonna use a 3904 and a 39.